Hey, how you doing? This section is very elementary. This is more of a review for those of you who maybe want to see thermal expansion. The coefficient of thermal expansion is given by this equation. So how do we use it? For the cases I will present, I will use the most familiar form of the thermal expansion. So this equation right here. Or if we are concerned maybe about the length of a metal bar, then I'm talking about this equation. The relationship between the coefficient of thermal expansion for these two equations is that beta is about 3 times alpha. Probably you can guess the relationship for thermal expansion of an area. I will introduce this concept by reminding you how mercury thermometers work. First I need a container, okay? Then I put some mercury in there, okay? At some initial temperature that I will define this to be my zero temperature. Or maybe you want to call it your room temperature. Whatever you want to call it. I'm going to call it 0 here. So any change in temperature will make the liquid contract or expand. If the temperature goes up, then the volume expands. Any change in volume will be related to the change in temperature and to the initial volume. The constant beta is a property of the material. Different materials have different constants, and this is why I'm able to build a thermometer in the first place. Because if all materials have the same coefficient, then the container will also expand, and then you are not going to be able to measure anything. Here I'm assuming that the expansion of the container is very small compared to that of the liquid inside. And that's exactly the case for mercury and glass. The extra volume here can be written in terms of the height, and then we can put it on the other side of the equation and solve for h. Notice that h is related to the change of temperature linearly. This, ladies and gentlemen, is what makes life very simple for you and me, because now every change in temperature by 1 unit will make this much of change in height. So these divisions are equally spaced, so everybody can read this. The next example has more algebra. Let's see. I have two metal bars, A and B, of equal length at some initial temperature, with different coefficients of expansion, of course, and they are bounded together. As temperature increases, one of these bars expands faster, and then it will create an arc. Then the question is, find the angle for this arc. So first I noticed that I can write the difference in radiuses in terms of A and B. These parameters indicate how thick the metal bars are. Then I noticed that the arc length is related to the angle, but this arc length is the final length of the metal bar due to thermal expansion, so these two equations are related. Some algebra here, and factor this, factor that, and giggity. Now the next example will be a little bit more interesting. It has some trigonometry. So imagine I build an equilateral triangle at room temperature with 2 bars of inbar and 1 of aluminum, like this. Then the question is, find the angle between the inbar bars as a function of the change in temperature. So at the initial temperature, the angle is supposed to be 60 degrees. Now I increase the temperature, and then the bars expand at different rates, and this is why the angle changes. So let me label things. This will be the original length, and this will be the increments in L, right here. This index I is for inbar and A for aluminum. So now let me look at this half of the triangle. We can relate the size of this triangle right here with this angle theta over 2. We can use some trigonometry. Now I can solve for sine of theta over 2 and replace delta LA and delta LI. And then finally I can just cancel the initial length, and we are done. You know, there is an easier way of doing this problem. Let me show you again. So we agree that at some final temperature the bars have expanded, and now the triangle looks like this. So let me use right here the law of cosines and solve for cosine of that angle. This looks much easier, but I have different answers here. Or at least they look different. Let's see if they agree. This one is cosine of theta, and the other one is sine of theta over 2. So first write sine and cosine of the same thing. So So let's write cosine as a cosine square of half of that angle. They look familiar. Notice that sine square plus cosine square equals 1. So these two answers are actually the same thing. Well, they are supposed to be. So I want to put some numerical values here and calculate something real. Let's calculate the maximum possible angle. This will be achieved right before one of the metal bars melts. So here are the melting points, and we see that aluminum will be the first one to melt. So this will be the maximum temperature. Let's use one of the results. I'm gonna choose this one, the one with cosine. And here you can use a calculator. I will use a program called Maxima. It's free and very nice. Hey, I want you to remember one thing. Remember that this model is actually an approximation, but a very good one. The reason is that when the temperature approaches to the melting point of the material, then the coefficient of thermal expansion is no longer a constant. So then you will have to solve the differential equation that I show you at the very beginning of this video. Okay? So take care guys, and see you next time.